Hi, this is Robert Quimby, and I'm going to tell you how you can apply least squares fitting to the problem of mapping XY positions into right ascension and declination positions. So when you take an image with a telescope, you're going to get the data off of your CCD, and it's not going to come with any information about what pixel maps to what position on the sky. This is something you have to calculate. What you do get is you just get pixel numbers, so you get column numbers and you get row numbers, and you get the values at each one of these pixels. And what you need to do, what you probably want to do, is map that into right ascension and declination position. So you want to know what is the position on the celestial sphere for, say, this star here. You know what the pixel coordinates are. It's 300 and 550, but what is the right ascension and declination in degrees? So the way that you can do this is you can say, okay, if I know that this particular spot in the sky maps to this particular XY position maps to this particular RA index on the sky, and then I have some sense that when I move a certain number of pixels, that corresponds to moving a certain number of degrees on the sky, then you have your transform. This is a simple linear transform, at least. So what you need to do is you need to come up with these scaling parameters. So first of all, you need to have your offsets, so you know what XY position corresponds to what RA index, and then you need to know your scaling, so when you move a certain number of pixels, how many degrees is that on the sky. So those parameters can be found using least squares fitting, and I'm going to show you how to do that. So first we're going to talk a little bit about the celestial sphere and how we can map the RA's index into XY positions on a plane. This is not entirely straightforward. There's different ways to do this. We're going to talk about one projection technique. We're going to write down a simple, just linear transformation to go from XY to RA index. That's going to be the equation that has our model parameters that we're going to fit for. Then we're going to get some data to work with. So we're going to actually get some XY positions on an image and get some RA index to go with those. And then using these, we can get our best fit model parameters in least squares sense. That give us those mapping parameters, and then once we have those, we can take other positions on the image, and we can in XY, and we can determine the RA's index for those. So first thing we're going to do is we're going to launch DS9. I'm going to use DS9 here. If you'd like to do this just with without DS9, just using Matplotlib, you can go ahead and do that. I've already got DS9 open, so next thing I'm going to do is load in this image. We're going to be working with example.fits in the media folder. And if I bring this in here, you can see I've just loaded that image there. So again, this is basically fresh off the CCD. We did do some processing of this image already, but you'll notice if you look at the WCS values here, they are not populated. So DS9 has no idea to know what the RA index of this position is. It just knows the X and Y coordinates as I move the mouse around. So we need a way to figure out how do we map from XY into RA index. So let's just talk about this problem a little generically here. So we have the celestial sphere, and that is a spherical surface, and what we have with our CCD is a planar surface. Now, how do we map positions on a sphere to a plane? First thing you have to acknowledge is that you can't do this perfectly. If you take a piece of paper and you try and wrap it around an orange or something, it's not going to work. You're going to have to bunch it up and fold it. There's not a simple mapping. That's just a mathematical property of a sphere. You can't map it directly on a plane. So we're going to do the next best thing. We're going to do a projection. So we're going to take positions shown on these red dots on a sphere, and we're going to map them onto this plane that we're our CCD, if you'd like. So keep in mind this drawing I just grabbed off the internet is a little bit backwards because the celestial sphere, of course, is around us. So you'd have to really picture this plane being inside the celestial sphere, because that's where your CCD is. It's inside the celestial sphere. But the same process applies. You have to map things from this kind of curved surface onto this flat plane. So one way to do this is to just take that piece of paper, if you like, or your plane, your CCD, whatever you want, and put that plane tangent to the sphere at some point. So in this particular example, they're using the pole here, but you could put this plane, across the side here or across the side here, wherever you want. But there's going to be one point of contact between the plane and the sphere. All right, so that point of contact is your tangent point. And from there, you can just map things directly just if you just think about them just going straight up, you can map it onto the plane. So this is what's known as mnemonic projection. In astronomy, we often call this a tangent projection. And the important thing to know is that there's a single point that touches on the plane that you're mapping to and the celestial sphere. So that's your tangent point, or sometimes we call it the reference point. So I may use that term in this tutorial. So you're going to map from the celestial sphere to that plane, but everything is going to be centered around this reference point. All right, so first thing we need to do is figure out the coordinates for that reference point on the celestial sphere and on the tangent plane. All right, so we can call these, so the RA and dec we'll just call R naught and D naught, and the XY position just X naught and Y naught. So that's our reference point. Now we have to figure out when we move away from that reference point, how do the values change? So when we move away from the right ascension and declination of the reference point to some new right ascension and declination, that means we're going to move away from our reference point on the plane X naught, Y naught to some other X I, Y I. So we have to figure out what this mapping is, and that means we need relationships between the right ascension and declination and these XY positions. Now, it's possible if you have your systems aligned perfectly that changes in X might be only changes in right ascension, or say it the other way around, that if you change your right ascension, you may just change your X coordinate. So you can think if you're just moving east-west, that's what right ascension does. Maybe you have your axis lined up on X, so that's all a change in one coordinate. But you could also have some rotation in your plane. So if you take that plane and just rotate a little bit on the sky, then changes in right ascension will also lead to a change in your Y parameter. So we're going to just keep these together. So we're going to assume that you might have a rotation and keep that generic. But we're going to stick with a nice linear relationship. So that means that if we start at some right ascension, R naught, and then we move away by some amount, so we started at X naught on the plane, we moved to Xi, that's going to change our right ascension by some amount, and the amount that it changes is dependent on the scale parameter A. This is telling us the mapping from pixels to degrees. So the units of this are degrees per pixel. You multiply that by the number of pixels you change, you get the number of degrees you changed, and thus the change in the right ascension. You do the same thing for declination. Keep in mind, for now, I'm actually not explicitly including the cosine term in this, which is okay to do, but if I wanted these to really be, the units of this to be angular changes and not just coordinate changes, I'd have to have a cosine term as well, but I'm going to ignore that for now, for simplicity. Okay, so what we can do is we can pick, we have the CCD image, right? We have this image, and we can say, okay, well, how about this spot right here? Maybe this spot right here. That'll be our reference point, right? We can pick whatever we want for our X naught, Y naught. So usually you pick something that's kind of in the middle of your image, but you could actually pick anything. You could even pick a negative number, something that's off the field, if you really wanted to. So we pick that point. That's our point, X naught, Y naught. And what we're going to need to do is figure out what these other parameters are. So we're going to need to figure out what is the right ascension and declination of that point, and what are these scale parameters A, B, C, and D. So I was highlighting this term A before, but also we have this term B in case we're not aligned. So these B and D terms have to do with, actually B and C terms, have to do with whether our XY coordinates are aligned with our RA and dec grid. All right, so we need to solve for these 6 terms. And we can do this if we can express this in this form here. So this is what we were talking about before on least squares fitting. If we can write an equation, a matrix equation now, y equals x times p, to represent this, then we know how to solve for p. So let's see if we can do that. This might not fit on the screen, but you should be able to see it on yours. So we can. Basically, we could, first of all, note we could do this one of 2 ways. So one is that we could fit just this equation just for right ascension, and then we can separately just do declination. What I'm going to show you down here is that we can actually do that all in one step. If we want to just build one equation based on both of these, we can do that. So the way we do this is, of course, we take our parameters. So let's start with R naught, A, and B. All right, and we'll put those over in our parameter matrix P as a column matrix. And then we want to have 1 multiplied by R, so that we can, R naught, so we can recover that. And then the next term, A, needs to be multiplied by this difference in X positions, this delta X. And then B needs to be multiplied by delta Y. So we take these first 3 columns, multiply them by these first 3 rows, and we recover this equation here, right? So, oops, see if I can scroll here. I lost my ability to scroll. There it is. R1 is going to be defined as R naught times A times this and B times this. Now, what I've done is I've actually put on these other terms in our parameters matrix, so we can do this in one equation. So I added the D naught, C, and D terms. Now in this first equation here, there are no D naught, C, and D terms, so all I do is I just multiply those by 0, and hey, those go away, and we get our nice equation for R1. And I can do that for all the other R right ascension values, R2, 3, 4, all the way to Rn. And then after I've done this, we can switch to declination and we can start working with this equation. So now this equation doesn't have any R naught, A, or B terms, so we set those to 0 in our matrix. And then we do the same thing. We have D, C, or D naught, C, and D. So we want to have a 1 for our D. We want to have delta X for our C. And we have delta Y for our D. And then you can see that we've now recovered this set of equations here. So then we can just put those in the remaining rows. So see what we're doing here. We started off with these first rows, just getting our RA part. The next row is getting our dec part. Again, we didn't have to do it this way. We could have split this and done this twice. But the reason I'm showing you this way is because sometimes you might have 2 equations like this, and they might have one term that is the same for both of these. For example, maybe this term B is equal to C. We want to force it to be equal. We don't want to fit 2 times because then it might come out with different values. So we could put this all together in one equation, and even though these other parameters don't apply, we can just add zeros to cancel them out, and then we can just fit the terms that are in common. So this is a nice generic way to do this, and it's good to keep in mind. So now we have it in this form y equals xp, and this is something we can solve. To do that, so all we need to do is just get some data and put it in and build our matrices, and then we can solve for those parameters. So we have this image that has stars on it, and what we can do is we can find XY positions. So if I just go to Edit, Region, and I click on a star, maybe I can center this a little bit better. You want to, if you're doing this, you want to make sure you're centering it as well as you can. That's close enough for now. And then you can double click on it, and it'll tell you the XY position of that star. Okay. We also need the RA index. So here's how we're going to do that. First thing I'm going to do while I'm here is I'm going to open up the header, and notice that there is an RA index listed here. This is where the telescope thought it was pointing. That doesn't mean that actually is where it's pointing, and it doesn't tell you what pixel that goes on, but this is roughly where the telescope should be looking. All right. So we can now open another window here. So I'm going to go to Analysis. And if you go down to Image Servers, there's a link to the DSS from Space Telescope Institute. There's others if you're in other parts of the world. I'm going to use this link here. It'll ask you to put in the right ascension and declination for a target and how big you want the field to be, and say arc minutes. So let's go ahead and do this using the RA index we have here. So the RA is 21, 19, 41.31, and the declination is plus 21, 57, 56.3. And so we can retrieve this, and this will actually query Space Telescope, and pull up our image. So ta-da! So we can see we actually have something that looks very similar over here, but first thing you may notice is that this is all upside down. And it turns out that our CCDs are read out that way. So in the normal orientation, you have north up and east to the left. You can see it by the cardinal points here. North should be up and east should be to the left. Let's flip our image here. So if I go to zoom, I can invert Y. There we go. Now we have something that looks a little bit more similar. The scale is different. You can see that this star and this star, probably this star and this star, and of course the galaxy is there. And this looks a little smaller than this. That's just because of the scaling differences. Let me make this a little bit bigger. I have to move it over here. Make this a little bit bigger so you can see a little bit more what's going on. So I'll just leave it here. Okay, so what I can do is I can now pick stars here, and then I can actually find it over here. So let's see if we can find that star. I think it's this one here, right? So I'll go ahead and mark that one. Oops, don't do that. And zoom in on it as best I can. Okay, that's pretty good. And now, this image, since we got it from Space Telescope, it's already been processed and it already has the right ascension and declination. So I can just look that up now. This is my right ascension and declination. And again, if I want that in decimal degrees, I can just use that and get it like that. So now I have, for one star, I have the XY position and the RA and dec. Okay. So what I should do now is I should pick several stars. So maybe I'll pick this star next. I don't have to look at it, just pick it and center it up as best I can. And then maybe I'll pick this star here. And that's pretty good. Okay. So I have those three stars here, and I can pick the same stars in the same order. Very important you pick them in the same order for what we're going to do here. And then you pick, let's say, this star here. There you go. So we have three stars on each one of these images. I believe those are the same stars. And so we have XY positions over here. We get RAs and decs over here. And so all we have to do now is to take those values and put them into our Python session, and we can get going. So there are ways to do this. You can start maybe on this frame here. If you go to region, you can actually save the region. Right? This will save it to your disk. And you'll ask you what format you want to do. I would name this something like DS9, maybe x.y or xy.reg. Put xy in here so you know it's the xy positions, and we'll use RD over here so we know it's the RA's index. Click OK, and then it'll ask you what format you want it to be in. To put it into Python, the simplest way is to do XY. It's just a two-column table. It's going to have your X values and Y values in columns. And then you can go ahead and save that to your disk. I'm going to cancel as I already got this, and do the same thing over here for your RAs and decs. And then once you have those two files, we can load those into Python. Okay, so this is what I was just describing there. Load those load those data files. So now we have those data on disk. We can load them into Python. We can use gen from text. So I actually have an example already provided where I have 3 stars that I did this for. You can do more stars. You can do different stars if you want. Make sure you do them in the same order, though. It's very important that the order stays the same. But for this tutorial, you can just use the same thing I'm going to use. You can use this example X, Y, and RD files. And so just use gen from text to load those in. And then the next thing we want to do after we have those loaded is we want to go ahead and define our tangent point, this x naught, y naught. We can put this anywhere we want, right? But normally when you're doing this kind of work, what you want to do is put it in the middle of your objects or middle of your data. So we want something that's, you know, around here. If we pick these 3 stars, let's have our tangent point be in the middle of those 3, right? So the way we can do this is we can just take the data. So remember how gen from text works. We're going to load these data into a NumPy array, and I'm specifying names here. So it's going to be a structured array where the first column is x and the second column is name y. So we can access, if we just work with xy data here, we can take the x values and then calculate the mean of them. And just give us the point in the middle. And we can do the same thing for the y values, xy data. We'll take those y values and calculate the mean. And we can run this cell, and it'll tell us that, okay, we're going to have a tangent point here at this pixel. Again, we can just pick any pixel we want. It's very convenient if you pick one that's near where your data are. All right, so now that we have our data loaded, we just have to build these x and y matrices so that we can solve our system of equations. So a good way to do this is to write a little function just so you can load in your data and it'll give you your matrix. So let's start with the y matrix. Remember, this is a column matrix. If we go back, this is going to be this column matrix here. So what it is we're going to have all the right ascension values and then all the declination values after that. All right, and it should be a column matrix. So to do that in Python, we're going to use the NumPy matrix function, and we need to pass a list of lists. And each list in that list of lists needs to be an RA value or a dec value. So let's do the RA values first and the dec values next. Keep things in order. We're going to pass this our RA values and our dec values, and it's going to do a for loop for each one of those RA values. It's just going to append each of those RA values. That's it. But we have to append it as a list, so we'll use the square brackets there and append the RA values. And then after we've done that, we'll append a list of the dec values, a list of a list. And once we have this, we have our list of lists, and we can return that as a matrix. Okay. So to call this now, we can actually take the data that we've loaded, and we have this RD data matrix, and we can pass it the RA values and RD data and pass it the dec values. And we can run this. So just to show you again, we just loaded RD data. I didn't specify this before. We did the same thing from our RD file with our right ascensions and declinations, and we named these RA and dec, the two columns. Okay, so we've got our Y matrix all set now, and we defined the function, we ran the function, we have the result stored in capital Y here. Now we do the same thing for X. So again, we're going to start with a blank list, and then we're going to append values to it. Now, in this case, we have a slightly different matrix. It's not a simple single column matrix. It has several columns in it. So let's go take a look back at what those should be. Let's go the wrong way here. Okay, so we want our matrix to have several columns. It's going to have 6 columns in fact. So we have 6 parameters we're fitting for. R naught A, B, D naught C, D. And so what we have is our first values for the right ascension are all going to be 1. Then we're going to have the difference between each x value and our tangent point in x, and the difference between our y values and the tangent point of y. And then we're going to have 3 zeros because we don't need these other parameters are not going to be part of this first equation. So we just put zeros there. So this is what each one of our RA lines are going to look like. So in Python, we can specify that by appending this list of values. So it's going to be 1 for that first column. Then we're going to have the dx value, the change in x. Then we're going to have the dy, the change in y. And then we're going to have 3 zeros, like that. So that'll take care of those first rows, which are for the RA. Then we need another set of values for the dec. So again, we're going to append a list. And in that, we're going to start now with 3 zeros because we don't need any of those RA terms. And then we're going to have a 1 for our dec naught, and then we're going to have the dx values and the dy values. Okay? So we append that, make our matrix, our list of lists, and then we turn it into a matrix with that function call there. And now we can call this. So we'll take those x values. So we'll take our xy data, take the x values, and we need to subtract off our x naught now that we've already defined. Same thing for the y values, xy data of y, and we'll subtract off y naught. Okay, so we'll run this, and now we have our x matrix defined. So we have y defined, x defined. We just need one more thing. We need to solve for p. So how do we solve for p? Well, since this is a linear equation that we wrote down, y equals x times p, we can solve it the way we solve any linear equation in using matrix math. So first thing we need to know is we had xp equals y, so we'll start with that, and then on the left side we're going to be multiplying to get rid of that x on this side of the equation. So what we did first was we multiplied by the transpose of x on the left to make it the matrix on the left square. And then we multiplied this whole thing by capital X transpose times x, all inverted. All right, so this is the same expression we did when we were fitting a line. We're essentially fitting a line now, but just keep in mind that this is a very generic equation. As long as we can use that, as long as we can express all of our equations in the form y equals x times p, then this is the solution to all of those. All right, so we'll go ahead and we can run this, and we have our solution. So we can look at what our values are, and there's our matrix giving those values. So remember the first value here in our matrix, that is our r naught, and this is now the right ascension of our tangent point. This value here, that's the declination of our tangent point. And this is our a and b parameters and our c and d parameters to get the transformation from pixels to degrees, change in pixels to change in degrees. All right. So we've solved it, and that means we can use it now. So if there's another star that we want to know the right ascension declination of, so maybe like this one here, I want to know what this one is. Right? I can just ask, what is the xy position of that? This is 519, 551. So I'll just put that in here. (519, 551). That's my x and y position, and I have to subtract off the x naughts and y naughts, of course. Oh no, I don't have to do that here. This is no, I do. Sorry. And that'll give me, I can run this now, that sets up my x matrix. And to get the predicted y values, all I have to do is take x and multiply it by the parameters we just fit. And there you go. It says that this is the RA index of that star. We can maybe do a quick check, see if that checks out. This is the star here. And I'll put this into degrees. And 7.6, pretty close. 5, yeah. There we go. So this isn't perfect, of course, because I just used 3 stars, and there's some uncertainties in where I put these circles. I didn't get them exactly right. So what you could do, of course, is now you have this initial guess. You can add more stars to that. You could do this by hand, but a better way would be to actually run a program like Source Extractor to get all the XY positions here, and then find all of the known RA's index of stars in the catalog, and use your initial guess that you've calculated with your p-values here to transform these xy positions into guesses of RA's index and see which ones match up. And then you'll get a set of positions that match. You can refine your search, go back, get a new p, do the matching again, find a new set of matched values, and refine your p again and again until you get the best value for p. And so that's it. This is just one example of how you can use least squares fitting. And enjoy.